All right, now let's discuss the nature of aqueous solutions. And we're going to divide solutions into three classifications. So the first thing you need to know is that the extent to which a solute dissolves in water is what determines whether and how much it's going to conduct electricity. Okay, so electrical conductivity is the ability to move charge, to conduct electricity. To conduct electricity, you have to have charge, you have to have electrons moving. In general, the greater the number of ions that you have dissolved in solution, the greater the conductivity. Okay, so the more charged particles, the more ions you have dissolved in your water, the more conductive that solution is going to be. So that is the basic principle by which we can classify solutions into strong electrolytes, weak electrolytes, or non-electrolytes. So let's start with the first classification, the strong electrolytes. As that name implies, these solutions are highly conductive. They are going to conduct electricity quite a bit. Many, but not all, soluble salts are, when they get dissolved in water, produce strong electrolytes. So you'll find that many, but not all, ionic compounds fall into this category of soluble salts that are eager to dissolve in water. So conductivity depends on solubility of the salt, and salts exhibit different solubilities. Solubility is defined as the mass of solute, for instance, you can measure it in grams, that can be dissolved in a given volume of solvent. So usually you'll see this expressed as grams of solute per, say, liter of solvent. So the higher the solubility, the stronger the electrolyte solution your salt can produce. Now, like I said, many salts, many ionic compounds are highly soluble. Not all, but many. Some of the examples of very soluble salts are sodium chloride, potassium chloride, potassium bromide, sodium bromide. We will learn solubility rules a little bit later, but I'm just giving you some examples right now. Calcium chloride is pretty soluble. Sodium nitrate is very soluble. A little bit later on this semester, we will learn which salts tend to be very soluble and which ones are only slightly soluble. So that's the first category of solute that can make a strong electrolyte. The second category of solute that can make a strong electrolyte are the strong acids. By definition, strong acids completely dissociate into ions in water. That's what a strong acid is. A strong acid is defined as a species that completely dissociates into H plus and whatever the counter anion is when it's dissolved in water. So there are lots of examples of strong acids, and you should know them all. HCl, HBr, and HI. So hydrochloric acid, hydrobromic acid, and hydroiodic acids are strong acids. H2SO4, sulfuric acid, is a strong acid. HNO3, nitric acid. And perchloric acid is another strong acid, HClO4. So all of these strong acids are examples of acids that completely dissociate in water, completely ionize in water. And that means if you take one of them and put it in water, for example, let's take HCl. If we dissolve HCl in water, it completely breaks apart into H plus and Cl minus ions. Okay, that's complete dissociation. The same goes for any of these other ones. Let's take, for example, nitric acid. If you put nitric acid in water, it completely breaks apart into H plus and nitrate. So lots of charged ions floating around in the water means that you're going to have a highly conductive solution. So strong acids make strong electrolytes, really good conductors. Strong bases are the same. Strong bases are also completely dissociate. So they completely ionize in water, complete dissociation into ions. And strong bases include all of the alkali and alkaline earth metal hydroxides. Alkali and alkaline earth metal hydroxides. So that's how you can spot them. Alkali metals are, of course, group 1 in the periodic table, and alkaline earth elements are group 2 in the periodic table. So that means that you have, for example, sodium hydroxide, potassium hydroxide, lithium hydroxide. Okay, those are all strong bases. From group 2, for example, calcium hydroxide, magnesium hydroxide, and there, of course, you have a 2-to-1 ratio of hydroxide to the cation. So when I say these completely ionized in water, what I mean is that, for example, if you have sodium hydroxide, that actually is a solid salt. You put it in water, it completely breaks apart into sodium ions and hydroxide anions. Okay, this reaction goes all the way to completion. Calcium hydroxide, for example, if you want to have a balanced reaction for its dissociation, you have to keep in mind that you have 2 calciums, 1 calcium, and it has a 2+ charge, but you have 2 hydroxides coming out for every mole of calcium hydroxide that you dissolve. So that would be a balanced reaction for the complete dissociation of calcium hydroxide in water. And you could write an analogous one for any alkaline earth metal hydroxide. The point is that strong bases, all of the alkali and alkaline earth metal hydroxides, are going to completely dissolve in water, and that is going to make solutions that are strong electrolytes. Now, sometimes you don't have complete dissociation. Sometimes only some of the molecules ionized when dissolved. And that creates a category known as the weak electrolytes. It creates a set of solutions known as the weak electrolytes. So primarily what we're talking about are the weak acids and bases. So strong acids and bases make strong electrolytes. Weak acids and bases make weak electrolytes. And what that means is that you're going to have weak conductivity. Okay, so they're not going to conduct electricity very strongly. Let me give you an example. An example would be acetic acid. Acetic acid is the acid that is in vinegar. This is a classic weak acid. It has this formula, okay, CH3COOH. And when it dissolves in water, the reaction doesn't go to completion. So we represent it with this double-headed arrow. And what that double-headed arrow does is it conveys the idea that this reaction only goes partially in the forward direction. And in reality, the vast majority of the molecules stay intact as CH3COOH. Okay, so most of the acetic acid molecules keep that H. They keep their proton. But only a very small fraction will ionize. However, because you have that small fraction ionizing, you will have some weak conductivity in your solution. Okay, so there are hundreds upon hundreds of weak acids in nature. Okay, acetic acid, citric acid, lactic acid, malic acid, just to name a few. Weak bases will also only partially ionize. For example, ammonia is an example of a weak base. So those kinds of solutions will conduct electricity only weakly. Finally, the last category of solutions are the non-electrolytes. And of course, as their name implies, they don't conduct. They dissolve fully, okay? So these molecules will dissolve in water, but they don't produce ions. They don't ionize. And for that reason, they can't move charge. The solutions will not conduct electricity. Examples include basically any polar molecule, sugars, alcohols. Okay, so sugar, for example, glucose is C6H12O6. This is a very polar molecule, so it will dissolve in water, but it doesn't ionize at all. So a sugar solution will be a non-electrolyte. Alcohols, for example, ethanol, CH3CH2OH. This is a very polar molecule, so it will dissolve in water, but it does not ionize. It keeps its proton, and an alcohol solution will be